to everyone. It's now recorded. Just to check, you can see the first screen, the first slide for everyone.
Yes, we can.
Yeah, okay. I can see that there's a large group. I'm very glad about it. And in the coming hour, I will talk about high impact weather, and especially the methodology we use at KNMI, which is of great help in forecasting convection. And I also welcome my Dutch colleagues from the Joint Meteorological Group in Woensdrecht from the military. I can see that also some colleagues from there in the meeting. And well, I will start with a short introduction. You know my name, Rob Groenland, and well, I'm working at KNMI for something like 17 years now, 17 years. I started my career at a Dutch commercial weather service in the 90s, the last century, as a forecaster, operational forecaster full-time. And then I moved to the KNMI in 2005, and now I'm working in daily life as a trainer. But I'm also involved in a climate advice group. So one day a week I'm also involved in the IPCC work. That's a whole different topic. That's on the topic of climate and especially climate change. But furthermore, I have experience as an operational forecaster for 20 years now. I do not do any shifts anymore at the moment, so I'm fully working during office hours. And as you can see in this slide, I do not only teach, I do not only give trainings on the topics of convection, but also synoptic meteorology, conceptual model, satellite meteorology, radar and mesoscale meteorology, and also dynamic meteorology. I just started with that topic as well. Okay, we are going to talk about a methodology that's called the ingredient-based forecasting. And I think for the next hour, my personal motivation is to give you a sort of feeling and also a lot of input to finally use this methodology in your own forecast offers, in your own work. And this methodology comes from the United States. It's based on an article that was published in 1996 by Charles Doswell. And basically, you can say that this methodology is based on looking at the atmosphere without looking at the black box. In the past, we were used by looking at all kinds of indices. And then you end up by looking in a sort of black box, and that's really not a motivation. I remember in those days that it was quite nasty by looking at all those indices to finally, yeah, make a sort of decision. Okay, we can expect some convection later on this day. So that is not satisfying. So this methodology will bring you to another approach in which you maintain physical insight. And you can say that physics works the same all over in the world, in the planet. And when the right ingredients comes together, then anything is possible. And the trick is that you look into those ingredients. And so that's in a nutshell what this ingredient-based forecasting methodology is about. And those ingredients where I was referring to consist of moisture, instability, and lift. And so those are the three ingredients we are going to look at in the next hour. And in the end, you also have to incorporate shear, vertical wind shear, and that determines the degree of organization. But that's you can look at it apart from the first three ingredients, because those are most important to find out where you can expect the development of convection. Well, at KNMI, we developed a convection forecast scheme. And in the upper part of this scheme, you can already see those three ingredients: the moisture, the instability, and the lift. And furthermore, you can see it splits into different sub-topics. If you look at moisture, you can look at all kinds of processes that has to do with evaporation and advection. And in instability, you can see a whole range of subtopics which influence instability, but also give you a sort of guidance by looking at the instability. And within lift, you can see all kinds of forcings that can lead to lift. That's step one. And in the forecast scheme, you can see in step two that you incorporate vertical wind shear. And that determines finally, in the end, the type of organization that will take place. You can see it here in the middle part of this slide. You can see the whole range from single cell up to the right part, the supercell. And in between, you can see all kinds of organization that has to do with the amount of vertical wind shear. And then, of course, you need to apply this knowledge in your forecast offers, in your daily work, in making a convective weather forecast, of course. So then you need to look at step 3 and step 4 by making a real forecast in terms of an estimate of wind gusts, precipitation rate, hail, lightning, and especially in the topics of convective wind gusts. I also have a module, and I will also embed that into a webinar. Not today, but that will be the next webinar on May the 2nd. So this first webinar is going to about the 3 ingredients, a little bit about vertical wind shear, and then the second webinar I will pay a lot of attention to step 3 and step 4. Okay, well, the goals, the key goals in doing this online course, and also, also following, also joining this webinar, is to help you as a forecaster in forecasting deep summertime convection with the help of this methodology. And I think what is very important, that's also my personal experience and also the experience of my Dutch colleagues at KNMI, is that by using this scheme, by using this methodology, you understand the physics behind this methodology. And that's the strength, really the strength of this method. And of course, you need, one of the goals is also to improve finally your convective forecast related to hazardous weather. Well, the schedule of this course, when you look into the Moodle and when you look at the online course, is that I start with giving you material as a sort of introduction in this ingredient-based forecast methodology. Of course, I pay a lot of attention in the identification of the 3 ingredients. So how to look at moisture, lift, instability on the hand of observations, but more by looking at NWP information. So what kind of information do you need to find out excess of maximum moisture, for instance, or where do you expect most of the lift in the course of the time, and where you can find most of the instability. So that's one challenge, and the other challenge is that you finally add an amount of vertical wind shear into your picture, and that's the part you need to determine finally the mode of convection. Well, when convection is going on, you can also look at, of course, satellite and radar signatures, so the remote sensing part. And in the end, you trying to more, converge into a quite detailed forecast about the amount of lightning, the peak intensity of the convective wind gust, There's a lot of interest in a lot of NMSs in Europe to have a methodology in which you can estimate the upper part of the convective wind gust. And of course, you also look at the limited area models you have. But this methodology is a sort of combination of looking at NWP information, so the LAM model output, but also the observations. That's really the strength. And in this webinar, and especially the webinar on May the 2nd, I will also pay attention. I give you examples of hail, heavy precipitation, and also a couple of slides about tornadoes. Well, the online course is consists of a few reading parts, 3 in total, a lot of examples, and also a quiz. And nowadays it's also thanks to Thomas Love, it's a self-made quiz, so you can do the quiz by yourself. My personal experience, and I also have heard that from last year's round, that the people really learn a lot about making this quiz. So there's really a learning curve in doing that quiz. It's not easy. It will take quite a bit of time, but please make that quiz during the spring. Well, today and May the 2nd, we have 2 webinars. And well, as a sort of estimate, it will take about 4 hours to go through the reading material per topic. So that's not the whole course, but per topic. Okay, I split the Moodle course into 4 sections. You can read it, of course, in your own time. And today's webinar again will merely go about the section 1 and also partly about section 2. Well, basically, you can ask yourself the question: where or what should you look for when making a convective weather forecast? So what information do you need? Well, you can, of course, you can look at a weather map, but it's not enough, but gives you a sort of first base information layer about the conditions in terms of air pressure and frontal systems. Well, what I think is very important is by completing this course, that you are able to estimate the degree of organizations and also the associated convective mode, but also that you have a more guidance in your daily work to estimate the meteorological impact of the convection mode, and also the moment at which the phenomenon occurs. Also, it gives you the ability to give a sort of estimate of the convection wind gust above what you can see in your limited area model output. Sometimes that can differ a little bit, so that's also important to do this course and to use this convective scheme. And well, that's the sort of following up that after following this course, you are also more prepared for looking at scenario-oriented frameworks for action based on convection mode. And well, to end this slide with, I think also a very important comment is that based on this methodology, you have a sort of a uniform way in looking at convection, and not only in your office, but I hope that also the other NMSs in Europe will take advantage of this methodology. Okay, to start with the basics. This is an example, and I'm sure that most of you have already seen this type of schemes in which you can see the basics of convection in general. This is an example of a single cell convection in which you have no wind shear or only a little wind shear. You can see the cumulus stage, and then the major stage in the middle part, and a dissipating stage in the right part. and it will take about half an hour or 45 minutes. Just as an example, because I will explain a lot more about it. It becomes more interesting by looking at incorporating vertical wind shear, and then you see that you can have types of convection which has a much larger time scale and also space scale. So that organization will lead to a sort of shift in the updraft and downdraft, whereby convection will can survive much longer than a single cell convection. But I will go into this in much more detail. Well, this is also my experience, that if you not practice your knowledge by doing an online course or by doing a simulation or by following a webinar like this, then at best you can have a convective weather situation in 25% of your time. So you have to be lucky by having such a weather situation while you have a shift. So hazardous thunderstorms are in the end quite rare to experience in your shifts. So then it is very important that you have some kind of training material where you can practice the knowledge. What is important is that you do not start a shift without trying to anticipate all possible weather phenomena. So that's important, that you can practice yourself through this kind of modules. Okay. So what should you do is that in the daily practice, when there is a convection going on or convection predicted during your shift, that you have a continuous diagnosis, and that the challenge is that you have to search for low probability and high impact situations. That's most of the time the case when hazardous weather has a high impact, that especially for an area forecast, that the probability most of the time is quite low. So it's important that you look for signs that those scenarios are starting to develop, and have a plan of action ready in case prompt action is needed. And I think the big advantage of using this convective scheme is that you already have a plan of action ready, namely that you are more experienced in forecasting that convection, so that you have time enough to activate all kinds of scenarios that has to do with informing stakeholders, your customers, the general public, the aviation park, the air traffic control center, etc., etc. Okay, to start with the theoretical part of this webinar, you can see this slide again with the so-called 4 modes of convection: the single cell, the multi-cell, the squall line mode in part 3, and the supercell mode in part 4. And well, my experience is also that each convective situation is always a little bit different in comparison with the former one. So it's always a challenge for each convective situation to carefully look into, for example, this convective forecasting scheme. And to start with step number 1, we are going to look at moisture, instability, and lift. And start with moisture. You can see on this slide that we are going to look at some parameters, which gives you more information about the amount of moisture there is in the boundary layer. We are especially looking at the boundary layer in terms of moisture, so between surface layer and 850 hectopascal. And then after this part, we are also going to look in the other ingredients. Okay, to start with the moisture. Again, evaporation and advection. If I go into a little bit more detail, You have a sort of diurnal change throughout the day. That means that when you have a clear day, then you know that evaporation is a very important mechanism in transporting water vapor from the surface layer into the boundary layer. And that's on a clear day. When you have a cloudy day, and especially when you have precipitation in the night or in the morning, and it clears out, then that means that there's quite an important flux of extra moisture in your boundary layer in the course of the day. And that's invisible because it's all water vapor, but that can lead to extra high values of moisture later on in the day for your boundary layer. So that's the diurnal change, variation, sorry, I have to say. And apart from that, you also have the attraction of, let's say, drier air or more moisture air from another place in your surroundings. So that can be a supply from a source area. Sea breeze is also a form in which somewhat more moisture air can be attracted from the sea into your land area. But when you are staying over land, then it's especially important to look at some source areas already in the morning when you start to make a convective forecast, by carefully analyzing your, especially your observations, because there can be a difference between your limited area model output in terms of an estimate of moisture and the real observations. And especially when you have to deal with some different days with convection, it can be very important by analyzing just the observations, because that can give you much more accurate information instead of looking at only looking at the limited area models, I have to say. Well, and then you ask yourself the question, and that's not an easy question, I have to say. How much moisture is too little, or how much moisture is enough? Think about that question. And there's also a link to instability, of course, but that comes into play in 10 minutes from now. So this is a sounding in which you can see that the boundary layer is very dry, and you have quite a deep convectively mixed layer, I have to say, up to some inversion around 500 to 400 hectopascal. So this is not a typical sounding for Europe, I have to say. So you really have to go to areas like Arizona or in the desert-like areas to have such an incredible dry boundary layer. So please keep this in mind. Well, I will come back to this, but we now go over to the second ingredient in this scheme, and that's instability. And for instability, we can look at different parts in your sounding. A very easy definition is that for instability, you can look at the temperature difference between your air parcel you can follow and the surrounding. So there are some indexes in the past which refers to that temperature difference. And that means that how larger the temperature difference, how larger the vertical acceleration you can expect. As you can see here, in this sounding, you have a capped boundary layer. So, if you, for instance, bring that parcel to above, then you can see that you have to overcome an inversion in the first place. And when you overcome that inversion, then you can see that in the free atmosphere, you have a quite an amount of difference between the temperature of the air parcel and the surroundings. So you can expect when you can overcome that inversion that you have a lot of vertical acceleration in the free atmosphere. And it's noted by a term called CAPE, convective available potential energy. So it's potential energy. So there must be in this example you need to overcome this inversion, and then that potential energy can be translated into a real energy that finally leads to a vertical acceleration of air parcels. Well, the energy of the inversion can be described as convective inhibition. That's the amount of energy that you have to add into the boundary layer to overcome the inversion itself, and that can happen in different steps. That can be due to the sun, diurnal variation, so that you can end up with higher temperatures, so that you can cross the inversion a little bit to the right of it, or you need some lift mechanisms that you lift the boundary layer, so that you deform the boundary layer so that the inversion disappears. So that's basically the two mechanisms. There's also another mechanism that can lead to the disruption of this inversion, that is when you increase the amount of moisture. But I will come to that with a few examples. Well, why is it so important to look at CAPE? Well, because there is a quite nice relation between CAPE and vertical velocity. So it's a measure of the rate of ascent. I have to say that this is only a rough estimate. You can see W max is the square root of 2 times CAPE. This is only a rough estimate because, as we will see, that there are also other mechanisms which act as a sort of damping, so that will lead to some lower values of this estimate. But anyway, as a sort of first rule of thumb, you can merely use this formula to have a sort of first estimate. Well, in this slide you can see that what I already mentioned, that it is almost always too high, because there are three mechanisms. There is no exchange with surroundings. That's called entrainment. There is no falling precipitation into account. That's called a water loading term. And there is no dynamic pressure perturbations. And if you look at the non-hydrostatic limited area models nowadays, those three mechanisms are nowadays indeed take into account. So that's quite luxury, I have to say, that within KNMI we're looking at our harmony model. That's a non-hydrostatic limited area model. And indeed, you can see an improvement in, for instance, estimating not only the rate of ascent, but also estimating the rate of descent. And that's important in estimating the peak heights of the convective wind gusts by incorporating all those three mechanisms. Okay, start with some interaction with you. It's a question for you, and you can use the chat for answering this question. You can see two soundings, A and B, and those two soundings have the same amount of CAPE. And as you can see, it's within those two soundings, it has a different distribution. And my question to you is, which sounding produces the strongest updraft on the basis what you have seen so far? So please fill in the answer. Yes, okay. You can see that people are trying to annotate. And yeah, I can see the answers coming in. And more or less, yeah, as I can see that, I think all of you, yeah, except one of two, they are giving answer A. Well, let's look at the answer. Oh. Stop annotating. Sorry. The correct answer is sounding A. Well, you have the correct way of thinking by looking at those sounding, despite the fact that there is the same amount of cape available in both soundings. You can expect some higher ascent motions, so stronger updrafts in sounding A, because a few reasons. It's more confined to a smaller layer, so RF parcels in that layer will accelerate more than in sounding B, where it is more spread over a deeper layer. That's one reason. And furthermore, and that makes it a little bit complicated, is that you also, when you look at the sounding, you can see, for instance, quite a dry layer in the upper part of sounding A. You also can see a relatively dry layer in sounding B as well, but in A it's quite obvious, quite striking, and so that you end up with a smaller effect of water loading. So when you sounding is really saturated, then you can expect a lot, quite a large effect of water loading, but in this case, the effect is quite small. And what you also can expect is some, less entrainment. But most important is that the amount of cape is more concentrated in a less deeper layer in comparison with sounding B. Okay, then the next question. Again, you have the same amount of cape. As you can see, it's in the same way distributed over A and B, but we have a different moisture profile. So again, the question: which sounding produces the strongest updraft? And think about the three mechanisms that can act as a sort of damping mechanism. Yeah, the answers are running in. Okay. Most of the answers you are giving is B, and there is also one or two participants who think that sounding A will produce the strongest updraft. That's interesting. I will give you the right answer, and maybe it's a little bit of a shock for you because both answers can be correct, and we have to think about it and to discuss it a little bit, because as you can see in the slides, an argument for choosing A, sounding A, is that in that sounding you can expect a smaller entrainment effect, while an argument for choosing sounding B for the strongest updraft is that in that sounding the water loading term is minimal. So we expect a minimal damping mechanism effect from precipitation, while in sounding A, the precipitation, the water loading effect is indeed much larger. So in the end, the answer can be both, and it depends on the strength of each factor. So you have the entrainment effect, you have the water loading effect, and as you remember, you also have a dynamical pressure perturbation effect. When you look in a non-hydrostatic model environment, those models are able to simulate convection explicitly. So that means that the vertical motions will be calculated based on effects like these. So the entrainment, of course, you need some kind of cape, but furthermore, entrainment, water loading, and again the dynamical pressure perturbation that you have to take into account, which will not take into account in a hydrostatic model environment. So for the larger model environments, the larger space scale models, normally they make use of a hydrostatic approach, but for convection, of course, you need to have a non-hydrostatic approach. So the answer again depends a little bit on the strength of the different mechanisms which can act as a damping on the first estimate of cape. Okay, by looking in a little bit more detail, when you talk about cape, then you have to ask yourself the question, by following a package of air or an air parcel, which air parcel is representative? Well, in practice, also at KNMI, in the morning, especially in the morning when we expect, let's say, afternoon convection, we have a discussion in our forecast offers about which kind of cape we are going to use. Not only in the observations, but especially in the numerical weather output. And at KNMI, we are looking at our limited area model output, but also at the ECMWF, and try to figure out which cape is representative to use. Well, we have three kinds of cape you can use. The SB, that stands for surface-based, the mixed layer cape, and the most unstable cape. And to give you an example of a surface-based cape, when you look at this sounding, by estimating the amount of cape when you lift an air parcel from the ground, you can more or less estimate then the amount of surface-based cape. And you are doing that by looking at the surface height, 1.5 meter, by looking at temperature and dew point, and to lift the parcel, and then you can see, following this scheme, that you end up in the blue area when you can find an amount of cape. Well, people who look at this sounding will immediately draw the conclusion that when nothing will happen during the day with this sounding, then it is of course not a really good idea to use surface-based cape, because you can see quite a nasty capped boundary layer. So quite a strong capping inversion, and especially between 900 and 800 hectopascal, you can see that an inversion will lead to a sort of capped boundary layer. So you need to look at other kinds of cape. Well, to start with the mixed layer cape. The mixed layer cape is especially used when you see in your soundings, for instance, in the early morning, that you have a sort of ground inversion. So that's not the inversion around 900 hectopascal, but it's the ground inversion in the lowest levels. And to mix the layer, you can get rid of that perturbation in dew points in the lowest tenths of meters. So in the lowest 10 or 20 meters, you have really a deviation from the representative amount of moisture by looking at dew points. So you have to mix the layer. And you can do that by mixing the bottom 50 or mix the bottom 100 hectopascal. And what you then have, you can see in this slide, you have some different kind of estimate of cape, because you can see in the mixed layer, you end up with a lower cape values in the end in comparison with the surface-based layer. But again, when you look at this sounding, it can be a typical sounding for the early morning, then it is not representative for the afternoon sounding, of course. But if nothing will change, then you have to apply a different kind of a cape estimate. That's called the most unstable cape. And that means that you try to ignore the gapping inversion with the knowledge that the gapping inversion is not disappearing. So then you have to take into account that you are going to look at the free atmosphere, so to speak, so that you look only at the layer where air parcels are able to accelerate upwards. And this type of cape can be important in the weather situations where you do expect it in the course of the day, because, for instance, there is a lift mechanism coming in, that the whole layer will be lifted so that the gapping inversion will disappear, and that indeed you are able to look at the cape values in the free atmosphere. Another example is that during nighttime, when you do have that gapping inversion and you have some lift just above the inversion, that also gives you a much better clue about the amount of cape that exists in the free atmosphere. And especially again during nighttime convection, there is a you merely have to look at the processes above the night inversion, so to speak. Okay, a question for you. We are going to look at 3 soundings. Can you more or less say for the left sounding to start with, which type of cape should you use? Start with the left sounding. Yeah, you can. Yeah, I can also see that you choose the right one. That's of course surface-based, and it's important that you already that you carefully have a look at how the variation in dew point with height in that boundary layer looks like. As you can see on the screen, you can see that it's already mixed. You can see that it's more or less mixed, this layer. So indeed, there's no inversion in the lowest layers. You can use the surface-based cape. Well, in the middle part, I think it's quite easy to determine the amount of cape. That I can give you the answer because it's not too difficult. But in the middle sounding, I should use the mixed layer cape, and in the most right sounding, I should choose the most unstable cape because there is an inversion, and with the knowledge that the inversion will not disappear, you can more or less look at the air layer just above the inversion. That's very important. Well, furthermore, cape is very sensitive to small changes in temperature. And you can, as you can see in this slide, you can see if you increase the temperature a little bit, then you end up with higher amounts of cape. But at the same time, you can also increase the amount of cape by increasing the amount of moisture. And you can do that by introducing a little bit higher dew points. In this case, in this sounding, it's a little bit dangerous to do that because, as you can see, it's not well mixed. So you probably can first mix this layer in the, let's say, the lowest 50 hectopascal, and from there you can add 1 or 2 degrees dew point increase. And then you can play around a little bit, and then you can see again an increase of amount of cape. And this is also a way in which you can erode or overcome the inversion by increasing both temperature and dew point. It is the best way to do. Then you can see that the convective inhibition will lower. So that means that that can lead to a situation in which the risk for the eruption of convection will increase, because how lower your sin, how higher the risk that for some reason, that can also be a little bit of lift, that can be then enough to overcome the whole inversion. Well, in our forecast office at KNMI, that's more or less copied also from the United States situation, but we have looked in some empirical data by looking at convective weather situations in the past, and we can merely look at those thresholds. So that means that for sin values, for let's say between 1 and 30 joule per kilogram, you can more or less expect convection. Again, you have to look at the diurnal variation in radiation, of course. That's in which you are able to estimate the maximum temperature. And when it is not sufficient to overcome that inversion by the diurnal variation, you can also look at some lift mechanisms. But for such a small value between 1 and 30, mostly it will happen that convection can take place. Well, the most important values are between 30 and 100 joule per kilogram, because then you need or strong warming. Well, you can calculate it, of course, based on the time of the year. You can calculate your maximum temperature. And when that is not enough, you really need lift to overcome that inversion. And above 100 joule per kilogram, it's convective inhibition. It's almost impossible to have convection. Well, typical cape values. Oh, sorry, that's not mentioned in the slide. But in summer period in Western Europe, but also in Central Europe, for quite high values of cape, you have to think about between 1,500 and 3,000 joule per kilogram. In the United States, in the Midwest, during the spring, you sometimes have 5,000 joule per kilogram. But in Europe, it's most of the time between 1,500 and 3,000 joule per kilogram. Okay, then something about the lift. That's a very important one, because as a forecaster, you need to have a look about forcing mechanisms. And that's at the same time also a very difficult one. It's also my experience that in the morning hours, or when you expect convection during night, you have to look at it in the evening hours. You have quite carefully look at the forcing mechanisms. And the question you have to ask yourself, how much forcing do you need which will lead to the eruption of convection? And in other words, how much forcing do you need to overcome the inversion? That's the main question. And as you can see in this slide, you have all kinds of forcings, like frontal systems. That's the most basic one. Quite a difficult one is the outflow boundary. You also need the radar information sometimes, but also the observations by figuring out where the location of outflow boundary is for some certain moment. Thermal troughs, sea breeze fronts can also act as a forcing. Of course, if you look at the dynamical part of meteorology, you need to have a look at the jet streak dynamics. which can also lead to extra ascent motion in the middle part of the atmosphere, sometimes also in the lower part of the atmosphere. Low level jet is also important to follow. When you do have relief or orography, hills or mountains, then you have to take that into account as well. Well, in the Netherlands, we have one advantage is that we do not have to take that into account. We are living in a flat country, except from the extreme south of the Netherlands in Limburg, and also gravity waves. And I have to say that for us as forecasters, the outflow boundaries, but also the gravity waves and the low level jets are the most difficult one to develop a clue about the amount of forcing. Well, lift is nothing more than a vertical motion due to the forcing. And well, maybe you've seen this, but on a synoptic scale, you normally talk about centimeters per second vertical motion. On the subsynoptic scale, you're talking about tenths of centimeters per second. But on the mesoscale, when you look at thunderstorms and when you look at convection, then you mostly talk about tenths of meters per second. And in extreme occasions, it will also exceed values of 50 meters per second vertical motion. Well, lift as a general mechanism leads to an overcoming of the convective inhibition. So that means that that you can have a transformation into kinetic energy. That's the vertical velocity. And due to large-scale rising motions on the mesoscale and synoptic scale, by lifting the air layer, the air will cool the battery, and then the capping inversion will disappear. Well, as you have seen in the former slides, you have different kinds of forcing. You have the most common one is the thermal forcing. That's just based on the diurnal variation you have. So that's also called radiative heating. So it's important that you have a clue about the maximum temperature that you can expect, but also at the same time calculate the convection temperature. That's the temperature mostly when you can overcome such a early morning inversion. And furthermore, you have the dynamic forcings. And that can be in the boundary layer at lower levels, but it can also happen in the upper layers. Well, as mentioned, in the lower layers of the atmosphere, you normally have to look at front, thermal troughs, outflow boundary, sea breeze fronts, low level jets, also the topography and the gravity waves, while for the upper air forcings you have to look at jet streaks, but also the PV anomalies, gravity waves. I have to say that for the upper air forcings, the challenge is to find out if those forcings are able to influence the boundary layer, because sometimes a jet streak will pass with some extra ascent motions, let's say between 500 and 300 hectopascal, but that will not immediately influence the vertical motions in the boundary layer. So sometimes it's tricky with respect to the upper air forcing. Okay, we still have 5 minutes. A little bit about that lift mechanisms. If you look at deep moist convection, it only occurs if a moist partial with positive cape is lifted above its level of free convection. Well, you can look at the traditional omega equation. You can see most of the important terms. If you are not familiar with it, but on the left-hand side in this equation, you can see an expression for omega. You can see it here, the term omega. And on the right-hand side, you can see merely two basic mechanisms. That's temperature convection. And then then you have to look at a sort of local maximum in a horizontal layer where you can find, for instance, most warm advection or most cold advection. And the first term on the right-hand side refers to vertical variation in vorticity advection. And it's quite abstract when you look at this equation in the first place, and that's where most of the forecasters will get a sort of headache, because you have to apply this in your daily practice work. Well, I'm trying to give you a few things out of this slide that can help you by understanding how the atmosphere works in terms of the importance of ascent motion, what it will do with your atmosphere. Well, again, the upward vertical motion is typically maximized where you have cyclonic vorticity advection, when it increases with height, and then you have a local maximum in your temperature advection. But I think it's much more interesting to look at this slide and the slides behind this slide. As you can see, as I told you, that the large-scale ascent is in the order of centimeters per second. And when you look at the mesoscale ascent, then you talk about lifting a parcel to the level of free convection. And that will take longer than a typical resident time of a parcel in the ascent regime. A large-scale ascent generally does not directly initiate storms. I will start with this sentence. But the ascent motion deforms the environment or primes the environment. That means that ascent motion will produce destabilization. That's a very important one. And a large-scale warm and moist advection modifies the local thermodynamic profiles. Well, as you can see that I mentioned it before, but this is in the form of another slide, that you can deform your atmosphere, for instance, by increasing your amount of moisture, as you can see in the middle, or increase your temperature, you can see on the right, but on the left, you can see what lifting means for your atmosphere. And that's what I mentioned in this slide, that the ascent motion primes the environment. So it produces destabilization. And you more or less can see it in this left part, in which you lift the atmosphere, which will lead to a destabilizing of the atmosphere. This is a very important slide, because you can see that there is there's a basic few of convective ingredients for active or deep moist convection. And as you can see on the left-hand side, roughly speaking, the first two parts in this slide, in this drawing, you can see moisture and instability. You can see that moisture, when you look at CAPE and synoptic advection, you can see that it has some interaction with the instability, as I explained. So through moisture advection or an increase in moisture, you can enhance the amount of CAPE. And that, if you look at the arrows, that influence the amount of instability. But at the same time, also there is some connection between instability and moisture. But more important is that the moisture itself can also lead to a smaller convective inhibition. And together with synoptic ascent, you can enlarge more or less, or prime the atmosphere, so to speak, for in the end an atmosphere where you can end up with deep moist convection. But still you need, that's the right part of this slide, some kind of lift. And that lifting mechanism, you need amount of triggering. That can be on the mesoscale, also on the surface. I've mentioned a lot of possibilities for triggering mechanisms, for lifting mechanisms. And that's a way to get parcels to the level of free convection. We're almost done, 1 or 2 slides. Again, a large-scale ascent movement is not immediately in the beginning a trigger for convection or shower, but it makes the environment suitable, unstable. But you still need some kind of lift mechanisms to overcome the inversion, for instance. So that's the reason why it is so important to follow all kinds of mechanisms that can lead to lift of the atmosphere. Well, this is a short introduction for the 2nd of May webinar, in which I will go in a lot more detail about the influence of vertical wind shear on the organization degree convection mode of convection. So this is for the next webinar on May the 2nd. And now I will go over to the questions. So I will stop sharing my screen. And together with Tomislav, I will look at the questions. Maybe you can also add some questions in the chat, but you are also welcome to ask me your questions live by using your microphone.
You need to raise a hand so I can unmute you.
Yeah, thank you.
Or just use the chat.
I realize that this is a lot of information in 1 hour, but I hope it can sink a little bit in your minds. And from Andrea, I hope I pronounce your name correctly, your first name. He asked how, okay. How can you see the degree of entrainment on the vertical sounding? That's a very good question, a very crucial question, because throughout this webinar, I think most of you have seen the sensitivity for the upward, but also for the downward motion, for the descent motion. And the sensitivity in relation to, for instance, entrainment, and also the other factors. Well, the entrainment, to have a sort of figure, of course you can use your limited area model, because nowadays those limited area models will take that entrainment into account. And what I know from the mesoscale development, that it's a combination of parameterization but also calculation. And nowadays in the non-hydrostatic models, we are trying to calculate it as a number, as a quite accurate number. So that's a way of looking into your model, but I have to admit that in our forecast office we cannot ask for those exact numbers. But so most important is that based on the soundings, you more or less divide soundings into atmosphere soundings where you can say this entrainment is large, or soundings where you can say entrainment, the amount of entrainment is low, or a sounding where you can say entrainment it's not quite accurate to draw a conclusion, so it's more or less in the middle. So it's quite nowadays quite a subjective estimate. So you do not really have an exact number that you can say, okay, the amount of entrainment is this number. It depends also a little bit on the exact development of the convection. If you for instance, produce a sort of proxy sounding based on the cumulonimbus cloud, where you're exactly in, then you have, of course, another amount of entrainment in comparison with a sounding you you make 10 kilometers or 20 kilometers aside, as you know what I mean. Okay.
I am not seeing any questions. Oh, there is one.
Oh yeah. Which ingredients do you know in terms of soundings to forecast lightning? Yeah, that's also a very interesting question. At KNMI, we use different kind of information that's merely nowadays based on model output statistics. So that's again a black box. I start this webinar by saying do not make use of a black box, but for some certain weather elements, we still make use of so-called model output statistics. And that's, I have to say, quite powerful methodology as a sort of extra help above this forecast convection methodology for forecasting lightning, because you need a lot more information than only cape instability and moisture. But on the other hand, there are some general rules in which you can say that how higher your degree in mode of convection, so organization in convection, how higher the amount of lightning. So for instance, supercell convection, but also squall line convection will most of the time lead to a lot more lightning than for the single cell and the multi-cell convection. The other question is synoptic lifting is never responsible for lifting. That's a question to me. And also in the stronger case, for example, a cold front. Let me think. Well, if you look at the synoptic lifting in the first place as a direct mechanism, then you can say that it is with a direct link in the first place not responsible. It's for the lifting. Let me think. Yeah, you mean, I think, Francesco, that you mean with synoptic lifting is never responsible for lifting. That you mean that synoptic lifting itself will in the first place not lead to convection, but first you need a second step, that is the deformation of your boundary layer and your mid-level of the atmosphere. And you have to wait for that process to take into account if convection will take place. So there are two steps. You have synoptic lifting. That will lead to destabilizing of the atmosphere. And then in the end, you have to find out if that is enough, that destabilization for leading to convection. I think that's what you meant with this question, Francesco. Yeah, okay. Yeah, another question from Franco. Could you explain a little bit in more detail the differences between the two radio sounders with the same cape but different moisture profile? Yeah, I can. What I can do is I can go to that slide again, and then go to that particular slide in which I showed the two soundings. That's this one, and the question was the question related to this question or the next one? I think you were referring, sorry, for this one, in which you have the same amount of K distributed in the same depth of the mid-atmosphere, and at the same time, the difference is the moisture profile. I think that's what you were referring to. Well, in general, you can say that when you look at sounding, and especially when you look at the distribution of moisture, then you have to take into account the entrainment and precipitation. Those are the two factors. You can say a little bit more about it when you look at the moisture profile. And for instance, if you look at moisture at sounding A, you can see almost saturated layer from above all the way up to the tropopause. So that means that you have in that saturated layer that you have a high amount of water. So precip water amounts are quite high. So you can expect a lot of precipitation on the ground in this sounding, based on this sounding in that atmosphere. At the same time, because the atmosphere is so saturated, the effect of entrainment is quite small, because you have a large saturated atmosphere with a lot of cumulonimbus clouds. So the little bit of entrainment effect, because there is entrainment, there's always entrainment, but it's very limited. While in sounding B, you have quite a dry mid-atmosphere. That means that you still can have cumulonimbus clouds, but then the impact of entrainment is larger, because the total air column is less saturated in comparison with sounding A. And again, when you look at sounding A, in the saturated layer, of course, you have the precipitation load, while in sounding B, the amount of precipitation is lower, is less in comparison with A. So therefore, the precipitation effect or loading effect is much lower than in sounding A. So I hope I answered your question. Yeah. But it's an important question, or I think, because the most in your daily practice work, you really have to take that into account. And yeah.
I'm not seeing any more questions.
No.
So just a reminder, all of this material can be found on the, oh, there is one question.
Yeah, from how you choose when you trust a sounding from a large scale model, for instance GFS, or a high resolution model like Cosmo, Icon 2.8 kilometers. Yeah, it's a very interesting question. Yeah, how to choose when you, well, if you look at the pre-convective environment, so in a pre-convective environment, I should say that for both models, so hydrostatic but also non-hydrostatic models, you kind of have a similar sounding, a similar clue. But especially when convection is going on in your model, then you better can choose your high resolution model soundings, because then it will take non-hydrostatic processes into account. So that's the answer. Yeah. Okay. When there are not any more questions, I would like to thank you all. We were in a large group, and I know that from my experience, 1 hour is quite long. But I hope you have learned a lot, and I wish you success in doing the online course. And do not hesitate when you do have questions to use the form. and I can use the form as a trainer, and well, and then I can answer your questions. And I hope to see you on May the 2nd in the second webinar. Thank you very much.
Thank you for the presentation.
Yeah.
And so, yeah, hopefully you join us on the 2nd of May.
Yeah.
And just before you leave, in the chat I have put the quick survey. It should take less than a minute. So if you would like to help us with the feedback, please go ahead. And all of this material is available to everyone on the EUMETCAL portal. Just search for the high impact weather course. You will need an account. And the recording will be available on the course page. And I think we can stop the recording.